Hey everyone, we are going to be doing a walkthrough of this problem. Which one is this? E-13. I've had a few requests for it. A lot of students are showing me some weird stuff with the energy. So I wanted to make sure and take the time and really talk about the energy stuff, but we might as well do all of it while we're at it. So if you need help with 7.1 or 8.1, this will be a good place to start. So what we have here is a ball. We have 4 points on the ball, A, B, C, and D. We're not told anything about point A, we're not told anything about point D, except that I think we can assume it's still moving 5 meters per second to the right. We are told that it's always moving 5 meters per second to the right. Now, don't mistake me. I actually think it's moving faster than that at A, because like if you have a ball that's going up, it slows down as it goes up, doesn't it? Like, I mean, right? Projectile motion stuff, right? So vertically, the ball is accelerating. Horizontally, it just stays 5 the whole time. So that's what we're going to work on, is we're going to do the projectile motion to start. So let's go ahead and make ourselves a little horizontal vertical chart. Horizontally, we know that this thing pretty much stays at 5 meters per second the whole time. There's no acceleration. And in this first bounce, we know it goes a total of 3.8 meters. So if it starts at 0, it ends up at 3.8 meters. So the question is, in this first bounce, well, how much time does that take? That's not too bad. We end up getting that position is equal to velocity times time plus initial position. Oops. So therefore, 3.8 meters is equal to 5 meters per second times t. T equals 3.8 over 5. Sorry, I'm trying to go a little fast today. I found that if I go too slow, no one watches the video. 0.76 seconds. So for at least for the first bounce, the time is 0.76 seconds. So let's think about how high it possibly can get. So if B is the highest point, that means it's just moving up. Now there's a few different ways to think about this, but I like using the graph. It was moving so velocity versus time plot, it's moving up for the first half of this motion, and then it's moving down for the second half of this motion. So this spot right here is as high as it's going to get. That must be spot B. So if this whole bounce is 0.76 seconds, it must be at spot B in half the time. You know that, I mean, it's a parabola. Parabolas are symmetric. The apex of the parabola will always be at the center of it. So this must be, yeah, so we have this 0.76. This must be then at 0.38. So I need to figure out how tall it's going to be at 0.38. To figure that out, we're going to need all of our vertical stuff. So vertically, our initial position is 0. Our acceleration is -10 meters per second squared. Our initial velocity, we don't actually know, but we can find that out. And then our, let's see, our final velocity here is 0. We know that's not moving up anymore at point B. And then its height, that's actually what we're trying to find. So I'm going to look here. I'm going to do this one graphically. Graphically, I know that this area of this triangle will be the height that this thing is under the ground. I also know that because this is gravitational, the height of this triangle is 10 times bigger than the width of this triangle. Well, I know the time, it's 0.38. So the height of this triangle must be 3.8. That's how, remember the slope of this line is our 10 meters per second squared acceleration. This must be 10 times taller than it is wide. So if it's 0.38 wide, it must be 3.8 meters per second tall. We could then go ahead and calculate the area of this. So if you have a triangle that's 3.8 meters per second tall and it's 0.38 seconds wide, 1/2 base times height, so 3.8 times 0.38 divided by 2, I get 0.722 meters. So I did kind of a combination of algebraic and graphical here. I hope that's not too confusing, but 0.72 meters. And I'm getting that from a lot of students, so that's good. So I'm pretty sure that this right here is 0.72 meters. We would go through the exact same process for point C. I'm going to save us some trouble, and I'm pretty sure I'm going to save us some trouble and just look it up, because I don't want this video to be a million years long. When I did this calculation before, I got, where did I get it? Where did I get 0. Oh gosh, where? Can I not zoom in? Can I not zoom in? 0.365. So 0.37 would be fine. So those are the heights we got, and I did the other one the exact same way. So we have now solved all the 7.1 stuff. The graphical stuff is a little tricky. Like I said, you could have absolutely have done the same exact thing using the two equations, v equals at plus v naught, or y equals 1/2 at squared plus v naught t plus x naught. You could have done all this fun stuff that way. Yeah. Now onto the energy. Now here's where we're running into some issues. So the first thing I'm going to do is I'm just going to go ahead and set up my LOL diagram. L, L, L. I'll put a circle in here. And this will be for point A, this will be for point B, and this will be for point C. So let's go ahead and first start by thinking about point B. I know it's some distance above the ground, and I know it's moving. So that means it must have energy stored in at least these two places. Energy stored gravitationally, because it's some distance above the ground, and energy stored kinetically, because it's moving. So I'll go ahead and do 3 boxes for this. Now I'll do 4 boxes. 4 boxes and 4 boxes. All right. Let's go back and look at point A. Now, the biggest issue I've had is I've had a lot of people tell me that this thing has the same amount of kinetic energy as B, right? I don't tell you how fast the ball is moving at point A, but I'm pretty sure if it's only going 5 meters per second, it doesn't go that high. It has to be going faster than that. So here, let's think about it energetically. It has all the same energy here that it does here. There's no new work being done. Here, let's say it this way. See how it has 8 boxes of energy here? I don't see anything here that can give it more energy. I've had a few people tell me that they think it does. I just don't know where it comes from. If this ball had rocket boosters, yes, I'd agree, energy going in. If this ball was kicked, yes, I agree, going in. But we don't have that. This energy must have already all been there. I think there's 8 boxes here. But those 8 boxes are not stored gravitationally, are they? See, look. It's not, it's right after it leaves the ground. It doesn't have any energy stored gravitationally. So I think it still has all 8 boxes, but all 8 boxes are kinetic. See, that's the big problem we're having, and maybe I wasn't explicit enough in my notes, but it's possible for energy of one type to be transferred into energy of another type. I think we've done that, like the puck going up the hill, that had kinetic energy that turned into gravitational energy, the same way this one did. Some of this energy that has stored kinetically gets moved over to gravitational. I think the tricky thing this time is I told you more information here, and you had to work backwards to figure out, oh, that energy must have all been stored kinetically before. Now, part C is a little different because it's going just as fast as it is in B. So I'm going to go ahead and put EK to be the same. But it's not as high in the air. So this must be different. I've seen 2 answers for this. I will accept either. The one that I put was that the energy is still there, but it's probably just stored thermally. You can imagine that every time the ball hits the ground, there's a little bit of friction. The particles start to move up a little faster. It actually warms up. That energy is actually stored thermally in the ground and in the ball. I have had a number of students give me the answer, though, that there's work being done. And that actually can happen, too. If this ball, when it hits the ground, if it pushes on the ground and makes the ground move, that would be considered work. And actually, ultimately, both answers can be the same answer depending on how you set up your system. I am fine either way. You just have to show me that there's energy that's not here anymore. So you could call this work. You could have stored it in ETH. Either way is fine. Now, I'm hoping for most of you that I'm making this video for, you already see where things went wrong. And I bet you do. And I bet you could probably turn off the video now and go fix it all. But just in case, I'll finish walking through it. So at point B, I have a ball moving 5 meters per second. We are told that the ball has a mass of, oh, I remember, I forgot to put this on the sheet. Oh no, let me go find it, sorry. Where'd you go? 0.20 kilograms. So we are told that the thing is a mass of 0.20 kilograms. So let's go ahead and add up our energies here. The energy stored kinetically when we're starting must be equal to the energy stored gravitationally plus the energy stored kinetically at point B. And that must be equal to the energy stored gravitationally plus the energy stored kinetically plus however much we did for work here. So this sort of equation that relates the three parts of the LOL diagrams is going to be really useful for us because now I can literally just start plugging stuff in. 1/2 mv squared will be equal to to mass times, oh, let's see, draw this a little bit nicer, mass times 10 newtons per kilogram times the height plus 1/2 mv squared. And that'll be equal to mass plus 10 newtons per kilogram, or not plus, times 10 newtons per kilogram times whatever height it gets to, plus 1/2 mv squared plus however much work is done. We don't know enough to figure that out yet, but we'll get there. All right, I'm going to go ahead. I want to find all this stuff at part B. That's going to be my goal to start with. Remember, ultimately, the goal is to find how much energy does the ball have stored kinetically at A. I think it's bigger than it is at B. And in fact, I'm pretty sure all the energy that we have at B will be stored kinetically at A. So let's figure out how much we have at B. So 0.20 kilograms times 10 newtons per kilogram times, and I believe we said 0.72 plus 1/2 times 0.20 kilograms times 5 meters per second squared. Multiply those out, add those all together, give me about 5 seconds. I get 1.44 joules. Yes. I can cut this out of the video, but what are you doing? I'm almost done. I'm so close. So this part right here is 1.4 joules. That's the energy we have stored gravitationally at B. Then this part over here, I get 2.5 joules. Any else trying to get work done with a 3-year-old around? It's fun, isn't it? So all the energy we have here, we have 1.4 joules stored gravitationally, 2.5 joules stored kinetically. Altogether, what is that, 3.9 joules? I think that we must have had 3.9 joules to start with. Now, if we wanted to, we could actually use it to figure out how fast ball A was moving. which is pretty cool because it actually saves us a ton of work from the same question answered using their 7.1 target. But yeah, I'm pretty sure that 3.9 joules, that's all the energy we have stored at point B. I'm pretty sure that's all stored in point A as well. So what's the difference in energy at point B and energy in point C? So we can do that. Well, let's just look down here at the math. The difference is whatever this W is, right? So we have to figure out, well, we're at a different height, 0.20 kilograms times 10 newtons per kilogram, but now we're only at 0.37 meters, plus 1 half 0.20 kilograms times 5 meters per second squared. These two are the same, so I'm just going to cancel them out on both sides. So it's the only difference is this is equal to this plus the work. So if I can find the difference between these two values, I should be able to find that missing work. And by the way, if you did it the other way, this would be ETH too, whatever you want to put there. So I'm going to go ahead. I'm going to find a value. Oh, we already know the value for this one. The EG is 1.4 joules. So I got to find a value for this. So 0.2 times 10, 0.37. I get 0.74 joules. So that's our energy stored gravitationally. Well, our energy stored kinetically is the same. So the only other place for that energy to go is right here. How much did we lose? I might as well make sure our units. Of course, I don't have. I get 0.7 joules. We must have lost 0.7 joules. The difference between the energy here and the energy here is just this W, and that must be 0.7 joules. I am not going to go through the bonus right now. You could figure it out. It's not that difficult comparatively. But remember, the major problem that we're having in here was this idea that we just threw a bunch of work in. And I don't think that fits the situation. Remember, if you do work requires force over a distance, meaning we need something to be applying a force to this ball over a distance. And that's why I purposely left it off the ground. See how it's after it leaves the ground? I didn't want this in contact with anything. That was very much intentional because I didn't want to worry about what was going on when it worked here, when it hit. All right, I'm hoping this answers your question. I'm hoping if you're someone right now who goes, oh my gosh, I did all this, I just forgot, I didn't know that I was supposed to do that. Sorry. It's a big conceptual thing. It's a really important process. And especially considering this looks so much like the ice puck, or the hockey puck that's going up the hill, or the roller coaster stuff. Yeah, I'm pretty sure I should be able to expect this of you, okay? All right, everyone. Have yourselves a great day. See you around.